Hello everyone, welcome to Homework Help. If you find the videos useful, please subscribe to the channel. So in this video, we'll solve this problem using the concept of derivatives. So as for the problem, determine points of inflection for the function and then sketch the function. So we know that points of inflection are points where the second derivative of the function is equal to 0. So the first step is to find the second derivative of this function, x to the power 4 plus 4x cubed. So we'll start by finding the first derivative. So prime of f of x equals, so for the first term x to the power 4, we can use power rule. So the derivative will be 4x cubed. For the second term, the 4 is the coefficient, so it will stay as it is. And for x cubed, the derivative is 3x squared. Now we can simplify this expression. So we can multiply 4 and 3. So 4 times 3 is 12. Now we can find the second derivative of this function. Which is the derivative of the first derivative. So for the first term, the coefficient is 4. So it will stay as it is, and the derivative of x cubed is 3x squared. Plus, so in the second term, the coefficient is 12. So it will stay as it is, and the derivative of x squared is 2x. Now we can simplify this expression. So 4 times 3 is 12. And then 12 times 2 is 24. So this is the expression for the second derivative. Now to find the points of inflection, we should set the second derivative equal to 0 and solve for x. So we'll sub in 0 on the left side. Now we can solve this equation. So we can start by doing common factoring on the right side. We can factor out 12x. So we get x plus 2. Now we have to solve for x by analyzing the two cases. So the first case is 12x equals 0, and we can solve for x by dividing both sides by 12. So the 12's on the left side get cancelled out, so we get x equals 0. So this is the first x value at which the point of inflection exists. Now we can solve the other case, and we can isolate x by subtracting 2 from both sides. So the 2's on the left side get cancelled out, and we get x equals negative 2. Now we can sub in these x values one by one in the given function to find the corresponding function values for these x values, because for point of inflection we need the x and the y coordinate of the point. So we can start with x equals 0. So we'll sub in x as 0 in the given function. So 0 exponent 4 is 0, and 4 times 0 cube is 0. So that means f at 0 is equal to 0. So the first inflection point we find is 0, 0. Now we can sub in x as negative 2 in the function. So f at negative 2 equals and negative 2 exponent 4 plus 4 times negative 2 cubed. Now we can simplify. So negative 2 exponent 4 is equal to positive 16, and then negative 2 cube is negative 8, and negative 8 times 4 is negative 32, and 16 minus 32 is equal to negative 16. So that means the other point of inflection is negative 2, negative 16. So this is the second point of inflection. So the first thing we can find is the change in the sign of the second derivative on the left side and the right side of these inflection points, so that we'll know whether the curve is concave up or down. So let's start with x equals 0, or we can start with x equals negative 2, so left side. So now we have to sub in x values which are on the left side and the right side of negative 2 to find whether the curve is concave up or down in the second derivative equation. So for the left side we can use x equals negative 2.1, and for the right side we can use x equals negative 1.9. So we'll sub in x as negative 2.1 in the second derivative equation because we are interested in the sign of the second derivative. So double prime of f at negative 2.1 equals, so we get 12 times negative 2.1 square plus 24 times negative 2.1. So now we can evaluate this expression. So 12 times negative 2.1 square and then plus 24 times negative 2.1. So I got a positive value. So I got 2.52, which is a positive value. So that means on the left side of x equals negative 2, the curve is concave up. Now we can do the analysis on the right side of negative 2.1, or sorry, negative 2. So now we can sub in x as negative 1.9. Now we can evaluate this expression. So we have to do 12 times negative 1.9 square and then plus 24 times negative 1.9. So I got a negative value, negative 2.28. That means the curve is concave down on the right side of negative 2. Now we can do the same analysis for x equals 0, the other x value at which the inflection point exists. So for x equals 0, so on the left side we can use the x value negative 0.1, and on the right side we can use positive 0.1. So we can use the equation for the second derivative. So double prime of f at negative 0.1 equals, so 12 times negative 0.1 square and then plus 24 times negative 0.1. Now we can evaluate this expression. So we can use a calculator. 12 times negative 0.1 square and then plus 24 times negative 0.1 So I got a negative value. So I got negative 2.28. So therefore, the curve is concave down on the left side of the inflection point at x equals 0. Now we can do the analysis for the right side. So we'll sub in x as 0.1. Now in this expression, all numbers are positive. So that's why we'll get a positive result. So the double prime of f at 0.1 will be greater than 0. So that means to the right side of x equals 0, the curve should concave up. So now we are done with the analysis for the concavity. Now we can find the intercepts for this function because that will help us identify a few points that we can show on the sketch. So let's start with x-intercept. So for x-intercept, we should sub in the function value as 0 in the given equation and then solve for x. So now we can do common factoring on the right side. We can factor out x cubed. So now we get two cases. So as for the first case, so x cubed equals 0. And now we can apply cube root to both sides. So we get x equals 0. So the first x-intercept we found is 0, 0. Now we can analyze the second case. So x plus 4 equals 0. Now we can isolate x by subtracting 4 from both sides. So the 4's on the left side get cancelled out. So we get x equals negative 4. So the second x-intercept is negative 4, comma. Now we can find the y-intercept. Now for y-intercept, we'll sub in x as 0. So both terms will become equal to 0. So f 0 is equal to 0. So the y-intercept is 0, comma 0. Now we can analyze the critical points for this function. So we should set the first derivative equal to 0 and solve for x to find the x values at which the tangent is horizontal. So for that we'll use the first derivative, and the first derivative function is the prime of x. Now we'll set the derivative equal to 0 and we have to solve this equation. So on the right side we can do common factoring. We can factor out 4x squared and we get x plus 3. So now we have to analyze the two cases. So the first case is 4x squared equals 0, which gives us x equals 0. So this is the first critical number, and the second critical number is so we get x equals negative 3. Now we can sub in these x values one by one in the given function to find the critical points at which the tangent is horizontal. So when we sub in x as 0 in the function, we already got the point as the x-intercept. So f at 0, 0. So the critical point is. Now we can do the analysis for x equals negative 3. So we'll sub in x as -3 in the function. Now -3 exponent 4 is equal to 81. Now 4 times -3 cube is equal to -108. So now we can subtract these numbers. So I get -27. So the second critical point is -3, -27. Now we can use all of this information to sketch the function. So first we can show the intercept for the function. So the x-intercepts are 0 and -4, and then -4. And the y-intercept is 0, 0, the origin. And then we found that the point of inflections are at x equals 0 and x equals -2. That means the concavity changes at x equals -2. And we found the critical points at x equals 0 and x equals -3. So -3 will be here. And the critical point is at -327. So let's assume it's here. So let's start the analysis at the origin. So as per the concavity analysis, so to the right side of 0, the curve is concave up, and there is a critical point at x equals 0, and there is an inflection point at x equals 0. That means there is change of concavity at x equals 0 and tangent is horizontal. So we can show the curve like this to the right side of x equals 0, and to the left side we can show like this. Now if we analyze the x equals -2 point for concavity, so to the right side of x equals -2, the curve is concave down, which we have shown, and then to the left side it's concave up. So we can show the curve extending all the way to the critical point at x equals -3. So we can see that there is a change in concavity at x equals -2. Now, since x equals -3 is a critical point and the x-intercept is at x equals -4, so to the right side of -3, the curve has to go upward towards the left side. Or if we go from left to right, the curve should pass through the x-intercept and go all the way down to the critical point at x equals -3. So this will be the sketch of this function. Now since we have to show that x equals 0 is a critical point, we should just edit the graph at x equals 0 to make it more flat, so that it looks like that the tangent is horizontal at x equals 0, like this. So this can be the behavior of the graph. I'll just edit it a little bit more just to make sure it looks precise. Yeah, like this. So now it appears that the tangent is horizontal at x equals 0. So these are the steps you have to keep in mind to solve a problem like this one. So I hope you'll find this video useful. Please share it, like it, and subscribe to Homework Help. Thank you very much and have a nice day. Bye.